Okay, we have a solenoid here. Suppose that the magnetic field produced by this coil is a rightward field. Then the front view will look like this. This looking like this from the front, so you get a rightward field. If you look into the coil, the cross-sectional view, then what you see is this, a magnetic field that goes into the coil. If we project the electron beam directly into the coil, then what you notice is these electrons will be traveling in a direction that is parallel to the magnetic field. When we travel parallel to the magnetic field, we do not experience any magnetic force. So with no force, the electron beam would just keep moving forward at a constant speed. We can also project the electron beam vertically in the coil. If we do that, then we realize that the electrons will be traveling in a direction that's perpendicular to the magnetic field. And we are familiar with this situation. This will result in a circular motion. So the electrons will keep circling in the coil. If you look from the front view, what will you see? You see the circular motion of the electron beam, but the beam will stay at the same horizontal position. It will not be moving forward because there's no horizontal component of velocity. It is most interesting if we project the electron beam at an angle into the coil. So how do we analyze the subsequent motion? Very easy. Just resolve this velocity into two components, the horizontal component and the vertical component. So the vertical component, as we have discussed just now, will result in the electrons doing a circular motion. But now, on top of this vertical velocity, we also have a horizontal velocity. This horizontal velocity, as we discussed earlier, will not result in any magnetic force, but it will keep pushing the electrons forward. So now what we have is actually the superposition of two motion. There's the circular motion, and this circular motion will keep going forward because of the horizontal component of velocity. Alright, so there's a circular motion that keeps going forward. So I think you can imagine the resultant motion. A circular motion that keeps going forward will look like this. This is called the helical path. If you try to sketch this path in the front view, right, in this view here, so it's a circular motion that keeps going forward at a constant speed. So what are you going to get? What are you going to see? You're going to get a sinusoidal wave. It looks sinusoidal from the front view, but it's actually a helical path. So in this question, we were asked to predict whether the electron beam will crash into the coil or not. So to decide on that, we will need to know the dimensions of the circular motion. So you have to realize that the circular motion has nothing to do with the horizontal velocity. The magnetic force, the centripetal force, is all decided by the vertical velocity of the electron beam. That's why when you do the calculation, when you calculate the magnetic force, the V that you use should be just the vertical component. Leave out the horizontal component. So after the calculation, we calculated the radius of the circular motion to be 1.2 cm. If you bother to sketch the circular motion, then it will be clear to you that the electron will crash into the coil. Because with a radius of 1.2, the circular motion will actually be quite big. The circle will look something like this. The circle is smaller than the coil, but then as you realize, the circular motion is not centered about the center of this coil. In fact, the extreme left end of the circular motion is at the center of the coin. So if you want to stay within the coin, what is required is the diameter of the circular motion to be smaller than the radius of the coin. So even though the radius of this circular motion is within the coin, but you see the circle will swing outside the coin. That's why our conclusion is the electron beam will crash into the coin. Alright, that's all I have to say. Ta-ta!